So today, I'm going to be talking about how Coursera started with ReST and actually how we've moved beyond ReST, how we've actually looked back to principles of databases, relational algebra, and SQL, and how we use that to help build an API and developer experience that we think is really far more productive than what we were able to do without it. So we're going to take you a little bit on a journey, and to start, we're going to start at the start. So I want you to think back to the dark ages, to about 2012. And so this is actually what Coursera looked like. Coursera was just founded. We had maybe all of a dozen different courses. Coursera is an open online education platform, or MOOCs, massive open online courses. And we had just been founded. We had like a dozen courses on our site from a couple partner universities. And we had some fun ones like machine learning and Dino 101. Our dinosaur course was really popular, really great course. Now, at this time, we were just a small team of maybe a half dozen engineers sitting around a table. Sitting around a table, and we're just like, we've got so much to do. We need to just get something up and out there. We had some great Python server-side developers, and we had some great JavaScript developers, and we were like, guys, single-page apps, that's like the thing. And so we were like, okay, great. Let's build a single-page app for our course catalog. And so we were like, okay, how are we going to do this? And we started by actually just doing the stupid, simple thing of we just created one API that would serve like the entire course catalog, the courses, the titles, the descriptions, the instructors, the partner universities, just everything in one gigantic API call, because it was actually not that gigantic. It was pretty small, and that was actually really great. The JavaScript developers got all the data. They could lay it out however they want. In fact, you could very quickly, our JavaScript developers, they were able to build a search page with really interactive faceting, and it was all really fast and really productive because all JavaScript, all client side, and this was really, really great. Until it wasn't. So we quickly developed a number of problems with this system, and actually the most important problem it's actually not the first one that you'd initially think about when doing something as naive as serving your entire course catalog in a single API response. The biggest issue was actually that our product needs changed. So what actually happened? When we initially launched, we had the courses. They were all for free. Anyone could take them however they wanted. And we got millions and millions of people to sign up, and that was great. And then we were like, okay, we need to figure out how to monetize. So what if we sell you course certificates as part of our signature track program, where you get an identity verified certificate? And it was really great. But the thing is, because we used this API, this one massive API, in multiple different contexts, multiple different pages, we couldn't really change it in a way that was natural to add in this signature track information. So we sort of bolted it onto the side, and it was a little ugly, but like it worked, and we moved on, and it was great. And then we got these sort of specializations or course sequences, and all right, we know how to bolt stuff on to these API responses, so fine, we did that. And then we really got stuck. So initially, we had assumed that all of our courses were going to be, put together by a single partner institution, a single university. And this held true for a long time. But then a couple of our university partners, they were like, okay, we want to collaborate together on this one course. We need both our course logos to show up. And that just broke everything. It was a big problem. And so, this monolithic API, it was actually the right decision at the beginning. It let us iterate, move really fast. It was simple. But the product needs ended up evolving faster than we could keep up with this sort of monolithic API approach. Additionally, as we grew more and more in our engineering teams, we weren't just sort of a half dozen people sitting around a table, but we actually had to split across multiple rooms, and we couldn't just yell at each other, or at least it wasn't quite so easy. And so we started to step on each other's toes in this monolithic API. Like one person wants to change it in one direction, another person wants to change it another way. And this didn't really work well either. And then finally, the problem that ended up really sort of killing us was, we started with this half dozen courses, and it was just a few kilobytes of JSON when we were serving this API. But then we got to over 1,000 and over that 1.5 thousand courses, and it turns out we were serving like a megabyte of JSON just to display that home page with just like 12 course titles and like the logos. It was absolutely ridiculous. So what are the key lessons that we learned out of this? The biggest is that scale matters. Now, Sure, scale matters in terms of data set size. As our course catalog grew, we had to do something slightly less naive. And that's something that we learned as we grew up. But scale also matters in terms of the number of queries per second, and in terms of how many users are using your site. And that's true. And scale matters in terms of the number of engineers operating on your code base. And scale matters in terms of the number of different clients accessing your APIs, in terms of, we've got mobile clients and web clients and third-party clients that are trying to scrape our course catalog data. But scale also matters in terms of what I call the number of types in your ontology. So what does this actually mean? Let's take an example of a company, Twitter, right? Twitter is a great service and whatnot. And when you think about Twitter, you've got tweets, you've got users, you've got likes and retweets. But you've got basically a small number of sort of things in your ontology and your understanding of the world, or at least of your product, right? If you take a company like Netflix, it's a little bit more complex, probably like an order of magnitude more complex. You've got movies, but you've also got TV series with different episodes, and you've got producers and actors and user ratings and previous watch lists, and it's a little bit more complex. There's more types in your ontology. I think Coursera is actually an order of magnitude more complex than that. So let me see if I can help illustrate that for you. Coursera has not just courses and course sequences and specializations and instructors and university partners and specializations and signature track, our identity verified product. But that's just actually our course catalog. Then when you go inside the course, you've got lectures and videos, but you've got quizzes and in-video quizzes, and you've got assessments and programming assignments and forums and exams, and it's even on top of all of that, you've got authoring, which is so much more complex than you'd ever realize when you're just looking at Coursera from the outside. And it's really, really complex. There's a lot of different data types, a lot of different things in Coursera's product universe. And this is something that we really, really learned over time as we had to scale our product. We had to scale in many, many dimensions. And I think we've had to scale in terms of the number of types in our ontology far more than we expected. And actually, I think quite a bit farther than many companies do. And so the solutions that work very, very well for 10 blue links or for a list of tweets don't necessarily inherently work if you're at a different point in the design space in terms of scale. So this was a very important learning that we had over time. Now, as part of understanding, as part of us sort of grappling and struggling with all these types in our ontology, all these different entities, we were like, guys, we really need static typing. Like, JavaScript, Python, those were cool in the 90s, but we need static types. And so, we actually sort of ran an internal competition. There's Go, there's good old trusty Java, and there's this hip new Scala thing. So we ran a competition where we tried out and built systems in all of these different languages. And Scala ended up winning, sort of my dark horse that I ended up backing. But Scala won, has a very powerful static type system. We picked the Play framework, backed by TypeSafe, the company that, or formerly TypeSafe, now Lightbend. So the company behind Scala has a great web framework, super powerful, exposed the full capabilities of HTTP. You could do gets, puts, posts, deletes. You can bind query parameters and path parameters and query bodies. You can parse them in an interactive or iterative manner, fully functional reactive. It was like, this is going to be great. Give us all the flexibility we need to handle all these different types in our ontology. So it turns out it was totally the wrong direction. It was absolutely counterproductive. We did not need actually that flexibility. We do need types. We do need strong static typing discipline, and Scala was able to help us there. But the full flexibility of HTTP was actually just adding more fuel to the flames. It was making it far more complex than what we needed in order to actually build our product. So as we started to adopt Play, we started to run into these issues. We realized that the Play framework wasn't going to solve all of our problems. So we're like, okay, what are we hiring an API framework? What are we doing when we're trying to solve this problem? Well, we're trying to basically get data from the server into our client apps as efficiently as possible. We want to be productive. We want to be fast and reliable and scalable. But the fundamental job we're hiring an API framework and service to do is to get data from our clients, or from our servers to our clients. Okay? Now, Coursera is actually, I'm very proud that Coursera has, despite being a very relatively young startup, has 3/4 of our user population accessing from outside the US. And these people are often accessing on 2G and on 3G mobile devices. So these devices have both very low bandwidth available to them, and they also have very high latency in terms of round trip and back and forth. And so that very much drove the fundamental performance baseline we needed to achieve in whatever API framework that we chose. And that is, we need to minimize the amount of data we send across the WAN in terms of just total amount of bytes. And we also definitely wanted to minimize the amount of back and forths. We couldn't basically get a list of course IDs, then basically make O of n queries to a course API endpoint. Then once we got those, we need to display the instructors, and then make O of n queries to an instructor's API. It's way too chatty, not going to work for us. On top of that, it would be very nice to have caching and e-tag support and even binary serialization that would help with sort of that minimum data transfer, but those were our two key driving points. As we thought about those, that actually pushed us to a fork in the road. We basically felt we had to pick which side of the fork we want to take. So what are the two sides? We thought one option is we build a custom, bespoke API for every experience, and this is sort of the experience-based APIs, and that would be just perfect, just customized exactly for that UI and that experience. So we'd have one API that would power the home page. We'd have a second API that did the course catalog search page. Another API would power what we call the course description page that has a lot more details about the course and the syllabus and whatnot. And we'd be able to customize it, and this would work really, really well. Unfortunately, we had a couple of things that gave us pause. We weren't convinced we wanted to go down this route. And the reasonings that we thought of is, first of all, we were actually a very small engineering organization when we were encountering these problems. And to be honest, we still are. And so we don't have the engineering resources to be able to build all of these different custom APIs as we rapidly evolve our product experience. We deploy code between 50 and 100 times a day. Most of these are very small changes. Some of these are very big changes. And trying to keep all of this in sync as we were trying to rapidly move with just a very small engineering team, we're very daunted by that challenge. Additionally, we were a little uncomfortable with this tight coupling between front-end and back-end teams. And we didn't have the ability. Some teams today are more sophisticated, and they have like back-ends for front-ends and running JavaScript and Groovy on the server for these front-end teams. We weren't able to build anything like that, and so we were a little concerned about that tight coupling. So that sort of pushed us to the other direction. What's the other direction? Well, it's sort of the opposite. Instead of one API for every different experience, what if you have one API, period? And you query it, and it gives back a different customized response based on the context in which you're querying the API. As we thought about this, we were like, OK, well, what does it even mean to be a queryable API? And then we thought basically, well, the front end, the clients, the web clients, the mobile clients, the third-party API platform clients, they really want to treat our back end, which is actually a distributed microservice constellation of spaghetti or beautiful hierarchy, depending upon your point of view. They really want to treat that whole thing as just a database. So what does it mean to even be a database? Well, we sort of scratched our heads and we're like, well, there's this whole new NoSQL revolution, but as it turns out, we're like, that was fun. We're going to do the new SQL revolution, right? So that's sort of where we are today. And so, the new SQL revolution is all about, fundamentally, it's hard to get away from math. Math is truth. And so the math that underlies databases is relational algebra. And so the three sort of salient points out of relational algebra, if you don't remember from your database classes, is you have projections, selections, and joins. So projections, you basically have a table of courses, and they have like, a bazillion different columns. And you can basically ask just for the course ID and the course title, right? So you can select some fields out of all the rows you want, okay? Selection basically allows you to filter the items in a collection. I want, from my courses table, I want course ID 3. Or give me all courses that match machine learning, right? Okay, so that's selection. And finally, joins is you've got this courses table, and you've got the instructors table, and you basically have some foreign keys between the two, and you want to write one query that gives you back the list of courses and the instructors for those courses, okay? And so we're like, all right, what would this look like in a JSON API in something like this so we could actually query? And we had a number of false starts. We took some inspiration from LinkedIn has a system called ReST, and this is sort of where we ended up. So we've got our courses endpoint, sort of like our courses table. And based on the query parameters, we're going to be able to show you how you can do those three main relational algebra operations. So we have what's called a finder, and I'll talk about the different kinds of views that you get into a relation or a table or a resource. And so under here is what the full URL would actually look like. And this is actually a live URL. You can go hit this right now on your laptops or whatever. So this is working in production and has been for a while. So you've got some query parameters. We're going to say we want to find all the courses whose slug is machine learning. Okay? In this case, it's going to be one course because this is an alternate foreign or an alternate key. And this is the response that we get back. Okay? So we get a minimal representation of the course, and it has the ID and a few common fields that you're going to definitely want. And we've got some extra metadata that we're going to ignore for the time being. So let's talk about that field projection. So you can ask, hey, I want the primary languages for your courses and for this course, and so this is how it fits in the query. And then it just shows up right there in the response. And so you'll notice that we have not just simple sort of primitive columns. We have arrays as part of our types, part of our fields. And that just turns out to be a little bit more productive for developers. OK, that's the easy part. Let's talk about the hard part. Let's say we want the instructors for our course. So you add it into the includes. It's a separate query parameter that tells us to do the join. And then as in this linked thing that we were ignoring from before, you can actually see the instructors, and you get, this is the instructor for the course. And you get it all in one response. It's sort of SQL-like. It looks very different in terms of the query parameters, but you're actually doing the same things as SQL. Now, as it turns out, this is sort of a fully recursive thing. So you can do field projection on the related objects, right? So you want the title for the instructor. And so you add it here, and you get it there in the response. So this is how we interact with our naptime APIs. This is how they map to relational algebra. And this is how we basically have one request that can do sort of a more sophisticated amount of work. And it's customized based on the request. So we're only sending the fields you ask for, plus or minus. And you can join things and get things all in one response, so you're not basically having a lot of back and forths. Okay? So I previously said we have a couple different types of sort of views into that table. So we actually inspired this a lot from REST, right? REST, you've got gets, but you've got posts and puts and deletes, and we have this sort of escape hatch in case you're doing something that we don't generally support in our relatively strict set of actions. But the reads is where we really focus a lot of our attention. Read performance and doing that in one request was very, very important for us. And so finders are your way of searching, filtering, alternate key lookup. Your gets are very important for having a unique URL and looking things up by ID. Get all is if you really need to scan over everything. But then multi-get is very important because that's actually what's happening underneath the hood when you have a list of courses, you need to get the related instructors. So we get those instructor IDs from the list of courses. Then we issue a multi-get against the instructor's resource, the instructor's table. So we can efficiently compute this fully joined response. Okay? So we spent a lot of time thinking about sort of that API framework, but it's very important to not ignore the developer experience. And so what is it like to actually implement one of these naptime APIs? And we had a number of false starts that we totally threw out, and we've iterated a lot on this. This is actually open source. This is taken exactly from our example service in our naptime open source repository, so you can compile and run this yourself. Starting from the top, we found that dependency injection is really the best way for developers to write and maintain these sort of sophisticated pieces of code. So you'll notice we tagged it as singleton and add inject. This is sort of juice or the JSX or JSR 306, whatever it is. Dependency injection stuff. We have our database abstraction, our data loading object. Fine, great. You extend from, so Scala has the concept of traits, which are like interfaces but with implementation. And Java 8 finally, like decades later, has that now too with Java 8. Great. So this is a trait. And it has some type parameters that define what is the type of the table, what's the type of the resource that you're inheriting from. Now we have this courier thing. That's actually our cross-platform schema language that has sophisticated code generation and schema validation. So courier is also available open source. It's a really nice project, has full IDE integration with IntelliJ, autocomplete. Been a lot of work to make that really productive for our developers. There's a lot more than just building a language. There's a lot of tooling that has to go along with it, but we've built that and that works really well for us. You then define the resource name. That's basically what shows up in the URL and the resource version. And then it's very Scala idiomatic code. We put a lot of work in figuring out what's the right way to translate these HTTP requests into Scala idiomatic code. So this is our get operation. You have an ID. It's just a parameter on your function. And then you basically have nap.get. So nap is short for nap time, right? The reason why we structured it this way is because you do nap dot. You always know you're going to start nap dot as soon as you're implementing a nap time API. And then you get this wonderful autocompletion in your IDE. We found that was really the best way for developers to learn and explore this nap time API for how you're building this very high level, very abstract sort of a thing. Now, there's a number of things you can do off of naptime. You can set authorization, you can do body parsing, you can do a bunch of sophisticated things there. And then you finally end with your naptime operation that you're doing. So we're implementing a get operation. And you get past the REST context, which has some authorization and authentication information. And if it's one of those write APIs, it has a body that's been fully parsed into a high-level type for you. Then basically, you just return as the last line of your closure. You just return the collection of elements that you want to return as part of your response. To hook this all up, we're using juice. So we actually do a funny thing. You have to inherit from a naptime module as opposed to a standard juice module. But it's standard, override the configure method to define your bindings. And you, instead of doing just bind your resource, you bind resource. And the reason for that actually, even though this code looks very sort of straightforward idiomatic Scala code, we're doing a number of tricks underneath the hood that you might not realize. So let's talk about them. This bind resource is actually not, it's not a standard method call. This is actually a macro. And the reason why we do that is because by using a macro, we're able to check a large number of things about your resource implementation to make sure that it's all conforming to our standard practices. So if you define get and your ID type is actually an int, and you have the wrong type here, we're going to fail to compile your project. We're going to catch this at runtime. There's no way you could ever deploy code or even really check it in that doesn't exactly match up. Additionally, as you're trying to return a collection in your response, right? You're trying to return a response that has one or many of the things. We actually verify that you're actually returning the right type. If you're implementing a get, you have to return a collection of 0 or 1 or an option of your resource type. If you're returning a finder, you have to return a collection of 0, or n. So we check all of this at compile time. You cannot implement a naptime API that is not wire protocol compatible. And this actually is really, really great. Additionally, we support default parameters in a very Scala idiomatic way. They're just default parameters as if you're writing Scala code. And when we've put in a lot of effort to make sure that we can both capture them for API documentation as part of the macro implementation, but also that they work, they parse correctly, and they parse very naturally. Additionally, as part of query parameter parsing, this is a boring one, this is just string, but we support a sophisticated higher abstract data types for every single component, every single user-defined type in this whole system. We found that higher level abstract data types, so you can have a course ID as opposed to just a string, and have additional logic and type safety with this has been hugely important to our developer productivity. The last thing I want to talk about is we realized that when you're defining these resource collections, you actually don't want to define them as a collection of a type. You want to define them as a collection of key value types. This took us a long time to realize, but once we did, we found that this was just simplifies so much about the implementation, making sure that everything's correct. So your collection is actually a collection of key value pairs which have the different types. Anyway, that's a little bit about sort of how we do this, but once you implement this, you get that field selection, you get that joining, you get a whole bunch of really nice properties, effectively for free, for very little code. And this has actually been really productive for our developers. In fact, this is actually what it looks like for adoption at Coursera over time. So the blue line is standard play controllers with the standard play tooling, and the red line is nap time resources. So these are, that whole class is a resource. You can have, multiple different nap time action handlers in one particular class. We're only going to count that once. And this code is actually a relatively old graph. I looked at it just over the weekend. We're actually well over 700 resources in the Coursera code base. And this I'm actually especially proud of because we didn't force developers to choose nap time. Developers at Coursera chose nap time themselves because it was the easiest, the fastest way to get things done. And actually, most importantly, because we had such a strict ontology, if you remember from this, we very much carefully define what is allowed to go on the wire and how it all looks. They actually developed a strong vocabulary in between our front-end developers and our back-end developers. They're like, our front-end developers ask our back-end developers, hey, I need a finder that takes this query parameter, and this query parameter, and everyone knew exactly what that meant. They could then go away, implement it independently. The client developer knew what the response was going to look like, knew how to interact with it, even though it hadn't been built. Server developer, knew exactly what they wanted to build, how to build it. No bike shedding, no should this go here, should this go there. It was all very straightforward, and this is a huge, really surprising boon to productivity. Just having a common language at a high level to really describe how to make these APIs go. So, as much as this has worked out really, really well for us, there have been some weaknesses. And in fact, the biggest weakness actually is that although we're able to automatically, at compile time, generate documentation based on the advanced types that we have in our naptime APIs, we didn't really do a good job of building a great tool to explore our APIs, even though we actually had all the metadata. And working with this flattened sort of response structure, even though it's very efficient on the wire, is sort of a pain to work with for our client developers. They've got to sort of match up all the foreign key IDs, and even though it's very common, very standardized, it was a bit of a pain. Now, about a year ago, Facebook came out and they were like, hey guys, React is great, and actually, we don't use just React. We use it with GraphQL. And we were like, this seems really interesting. Now, we've adopted React very aggressively at Coursera. It's been a huge help for us. And one of the pain points with that has been, all right, how do we do this data loading and data fetching on the client side? And as it turns out, GraphQL works really, really well for this. So, in fact, one of the most important things of GraphQL is its in-browser IDE called Graphical. And it has auto-completion and everything fills in. It's type-checked because GraphQL is very schema-driven. And this actually turns out to be a huge boon for client developers and to client developer productivity. And so I'm very pleased that we're now moving towards GraphQL. Now, how does this actually all work? We're absolutely 100% sticking with nap time on the server side. We love it. It's working really, really well for us. And so what we're doing is we're actually building this translation layer, that we actually are able to define a bijection between GraphQL and our naptime HTTP servers. And so the request comes in. It hits the assembler service, which has this GraphQL understanding. It will then take the request and say, aha, you are making a request, and you want the profile for the user. You also want the enrollments for that user. And for those courses that the user's enrolled in, we want to get the course description and the instructor. And so the assembler service basically orchestrates all of this. And this is only possible because naptime has such a strict understanding of everything. We're able to machine sort of merge together all these sorts of things. And this is actually what we're moving towards today. This is, we're putting our first GraphQL applications into production. And this is a very exciting time for where we're going. We really think this is going to really help us scale, both as our developer organization grows and as the types in our ontology continues to just explode. Now, there are a number of key lessons that we've learned. The first is carefully understand your problem. Right? We thought that types were going to be our solution, and they were a part of our solution, but they were definitely not the whole solution. We took sort of a bit of a misstep when we just adopted play directly. That didn't address the key problem. Second thing that we've learned, we've been able to build a lot of things on our own, but it's hugely beneficial to plug into the ecosystem. We're really excited to be working with Facebook on GraphQL and with Apollo, the Apollo Stack team, Graphical. It's been a huge boon in productivity for us to plug into the ecosystem. Developers come in and they already know these tools, they love them, or at least they know about them, and we're able to benefit, share code back and forth. This has been really, really important for us going forward. And finally, as much as we get excited about the hot new latest and greatest technology, a lot of things are sort of just coming back around again. Anyway, so stand on the shoulders of giants by looking to past work and applying them to your new problem. Anyway, thank you very much for listening to me ramble on this evening, and let me know if you have any questions.